Good evening, everyone. Welcome to this lecture on static analysis for voltage stability. We have already seen the dynamic analysis for voltage stability. So let's have a recap on the dynamic analysis. In the dynamic analysis, we had the rate of change of state variables, or the representation of state vector as its rate of change, was equated to f of x comma v, and I of x comma v is equal to yn into v. Here I was the current injection vector, the current injection vector. Then x is the state vector of the system, state vector of the system. So by this x dot representation itself, we can understand that we are interested in the dynamic analysis, because this is rate of change of state variable with respect to time. Rate of change of state variable value with respect to time. We are interested on x dot. Now V is the bus voltage vector. Bus voltage vector. And Yn is the network node admittance matrix. Okay, so in the dynamic analysis, we can analyze everything about the current state of the system and the dynamics of the system, or the dynamics through which the system is going on at the operating point under consideration. That we'll be able to analyze using this analysis. Now we are moving on to static analysis. In the static analysis, the additional information we get is the margin to instability. In the dynamic analysis, this information is not there. In the static analysis, we should know that to what extent the system can tolerate the disturbance without being unstable. Here, instability is with respect to voltage only, so without being voltage unstable. Okay, that is a consideration. Now, there are two types of static analysis methods used for voltage stability analysis. The first one is VQ sensitivity analysis. VQ sensitivity analysis. And the second one is QV modal analysis. QV modal analysis. QV modal analysis. Now let's see what is this VQ sensitivity analysis first. Then we will move on to QV modal analysis. In the VQ sensitivity analysis, we are interested in finding the vector delta P delta Q equals, this is the Jacobian matrix. So the elements of Jacobian matrix is J P theta, J PV, J Q theta, and J QV. So what should be this vector? This vector should be related to, so P and theta, we are relating PQ with theta and V. So basically this is power, right? This is voltage. So this is complex power. Complex power in the sense we have real and reactive power. This is complex voltage. Complex voltage. So we have both magnitude of V and angle of V. So this is theta. So how these variables are related with respect to each bus? We know that there is a strong coupling between P and theta, right? P and theta, and there is a weak coupling between Q and theta. There is a weak coupling between P and V. There is a strong coupling between Q and V, right? So all these relations are taken into consideration with this static analysis. So this Jacobian gives the sensitivity of these variables with respect to the variables in the LHS or vice versa. So that is the importance of Jacobian, just like what we do with the Newton-Raphson load flow analysis. So here in the static analysis, the system snapshot is captured at various time frames along the time domain trajectory, and at each time frame the time derivative of the state variable is assumed to be 0, which means this is the time derivative of the state variable. In dynamic analysis we have seen x dot. So x dot is assumed to be 0. There is no rate of change of variable value with respect to time in static analysis. Okay, so this is the assumption. Assuming this, we are capturing the snapshots of the system at different time frames. Okay, now the state variables take on values specific to the time frames, and consequently the overall system equations reduce to purely algebraic equations, because this x dot is completely removed. X dot is 0, right? So it's completely converted to algebraic form or algebraic equations, allowing the use of static analysis techniques. What are static analysis techniques? Load flow is a static analysis technique, because if we assume a particular bus as PQ bus, we assume that there is no P dot and Q dot, right? There is no change of active power with respect to time or change in reactive power with respect to time. Rather, we assume both active and reactive power assigned to a particular bus as constant. So this is one static analysis. Available transfer capability estimation, ATC estimation, is another static analysis tool. So there are a lot of static analysis tools in power system. So these static analysis techniques could be used if we assume the rate of change of state vector is 0. So we are not going for a dynamic analysis, and we are confining ourselves to static analysis to understand the distance or the margin towards instability. So stability is determined by computing the PV and QV curves at selected load buses under consideration. We have already seen the importance of PV and QV curves. In the PV curve, we have seen the collapse point. The loadability of the system depends on the PV curve of the system. Then in the QV curve, we analyzed the slope of the curve to determine the stability at different operating points. So when we had drawn this QV curve, we assumed active power to be constant. Then we vary only Q and V, Q and accordingly V, right? Corresponding change will reflect on V. So such curves are generated by executing a large number of power flows or several power flow executions are done to draw such curves using conventional models. So these procedures can be automated, but they are time consuming and they don't readily provide the information useful in gaining insights into cause of stability problems. So, and these procedures confined to individual buses. The stability characteristics are established by stressing each bus independently. By the term stressing, what we mean is if you are incrementing the load step by step at a particular load bus, what happens to the voltage of that bus? That is the analysis. So this may distort the stability condition of the system. The information, distort the information on stability condition of the system. The buses selected for QV and PV analysis must be chosen carefully, and a large number of curves, PV and QV curves, will be required to get the complete information on voltage stability of these buses. So, but we have a problem with running the load flow algorithm. Every time the load flow algorithm will not converge, it may diverge also. So when the power flow algorithm diverges, we will not be able to find a feasible solution, network solution. That is another disadvantage of doing this load flow based analysis, or rather we have this repeated load flow. What is repeated load flow? Repeated load flow in the sense we assume that the load bus is PQ, but if we increment the active power, so in the next step we take P plus delta P. Then again we'll run the load flow, and again in the next step we'll make it P plus 2 delta P. So like that we'll repeatedly execute the load flow algorithm. So this is what is repeated power flow. This is one method which is used for finding the available transfer capability of a line. Anyway, that is not in the scope of our course, so I'm not going to that. If you are interested, you can see some literature on that. Now, we will move on to the quantitative side of VQ sensitivity analysis. So this delta P and delta Q, which are shown here for static analysis, this one, the delta P and delta Q shown for the static analysis, this can be considered as increments in active and reactive power, or incremental change in real power and reactive power. And this delta V and delta theta are assumed to be the incremental changes in voltage magnitude and voltage angle. And the network Jacobian matrix associated with each bus is very important for analysis of voltage stability. This is the Jacobian. This is the Jacobian matrix, because this gives the relation between these two. Right. Now, based on these considerations, we take that delta Q equals JR into delta V. What is JR? So while analyzing the variation in reactive power, we assume the variation in reactive power as 0. That is delta P equals 0 is assumed, and we are analyzing delta Q. So delta Q equals JR into delta V. Here JR means the element inside the Jacobian which is relating Q and V. Okay, the element inside Jacobian which is relating Q and V. Okay, now JR equals JQV, then minus JQ theta, JP theta inverse, P theta inverse, and JPV. Okay, So JR is the reduced Jacobian matrix of the system. Why we call it as a reduced Jacobian matrix? I'm not going to the derivation here. Here we have relation between QV, Q theta, P theta and PV. But the condition here is delta P is 0. The variations in active power is assumed to be 0. That is why this is known as the reduced Jacobian. Our full Jacobian is here. Okay, this is the full Jacobian. Now, if we take the inverse of JR, if we take the inverse of JR, what are you going to get? This is JR, right? If we take the inverse of JR, we will get the QV sensitivity, right? The matrix JR inverse, the matrix JR inverse is the reduced VQ Jacobian. Reduced VQ Jacobian. Or if we take JR inverse, Q will go to this side. JR inverse will come to this side. So this will give you delta V by delta Q, kind of delta V by delta Q, which is VQ sensitivity. VQ sensitivity. And we have already seen in the QV curve that positive slope corresponds to, what is positive slope? If we inject more reactive power to a bus, you are expecting an enhancement in voltage profile of that particular bus. That means the direction of voltage and reactive power are in the same, they are in the same direction. So we assume a positive slope there. But instead, if we see a negative slope, it's an abnormality and we take it as an unstable condition. So the condition for stability depends on the VQ sensitivity. From the QV curve, we have seen that. The same thing we apply here. So for each bus, we have this VQ sensitivity. If we take for ith bus, if we consider it for ith bus, then delta Vi equals JR inverse into delta QI, right? Now, if it is a vector, we have delta V1, delta V2, etc. Right. So for each bus, this is for first bus, this is for second bus. Here also we have delta Q1, delta Q2, etc. So for each bus, we have QV sensitivity, the VQ sensitivity, not QV sensitivity, VQ sensitivity. So for the VQ sensitivity at a bus represents the slope of the QV curve at the given operating point. A positive VQ sensitivity is indicative of stable operation. The smaller the sensitivity, the more stable the system. Right, because with small variations in Q, there is corresponding variation in V, means control is easy. It's simpler, right? But if there is drastic sensitivity, then it's more of an unstable operation. It's not unstable, but it's less stable, right? It's less stable. Now, as stability decreases, the magnitude of the sensitivity increases. So the VQ sensitivity increases and it becomes infinity at the stability limit. Or conversely, a negative VQ sensitivity is indicated. A small negative sensitivity represents a very unstable operation. Now, because of the nonlinear relationship between V and Q, the magnitudes of the sensitivities for different system conditions will not provide a direct measure of the relative degree of stability, because we assume it as incremental disturbances and we are linearizing around the operating point. We are not taking it as nonlinear as such. So that is why this assumption comes into picture. So this is the importance of VQ sensitivity, the negative VQ sensitivity and the positive VQ sensitivity, how it indicates stable and unstable operation. Now in the next lecture, we will move on to the second part of static analysis, which is the QV model analysis. Thank you.